So I will start by talking a little bit in general about how we model things in cognitive science. And traditionally, during the first decades, we had this kind of symbolic modeling. Everything was written in some form of language, natural language or computer language. There was programming languages, is what logical formalism. And the basic notion was what's called a predicate or a variable in the programming language. And then there were kind of logical and syntactic operations, corresponding operations in programming languages. And that was the basis for the first phases of AI and for first phases of cognitive science. But there were some problems with this, and one was, where do the predicates come from? I mean, in general, they were provided by the philosopher or the linguist or the computer scientist, and it was never discussed, or very little discussed, how we can learn the predicates that we work with. And then another problem that showed up in inductive reasoning was that all predicates were treated as equal, and they are not, and some are more natural than others. And I will talk quite a lot about the natural, makes a concept natural here. So that was the first wave of modeling in cognitive science. Then in the 1970s, we got something called connectionism. And then we have neural networks as the main models here. There were no distinct symbols, there were no syntactic operations, but there was learning in distributed representation. There were dynamic connection weights. The neural networks were shown or given a lot of inputs, and they changed their connections, and thereby they could learn. And they could solve problems. In particular, they solved problems of categorization, and that thereby creating concepts in some way. But there are problems with this approach as well. And one is that they are very opaque. We don't really, very seldomly know exactly what is represented in the network. They were very sensitive to the data they were presented with. So there were different kinds of biases in their learning and so on. And for most methods, the learning is very slow. I mean, you have to update the connection weights very slowly. Otherwise, the neural network becomes very unstable. Then I and other people proposed a third approach, and that is what I call the conceptual spaces, or we can call it the conceptual level, which is some kind, in terms of granularity, in between the symbolic models, which were kind of high-level linguistic models, and the connectionist models that are low-level based on neural connections or models of neural connections. My proposal is to have something in between that is more geometric, based on a set of dimensions. You can call them quality dimensions if you're focused on perceptual mechanisms. And the mathematics here is basically using geometry and topology and vector modeling and stuff like that. It's a different mathematical structure that underlies the models. So the basic building structures are dimensions in domains. I will talk more about that in a second. But the main problem is, of course, that these dimensions have to be given to the system somehow. I mean, if you work with connectionist models, you can generate dimensions. I mean, you can find ways of analyzing the networks that somehow generate these spaces, but well, that's not done always. So I will not talk very much about this problem today, but I will present you the theory of conceptual spaces. So first part is based on my old book that Manuel mentioned from 2000 on conceptual spaces. And the basic idea is that we organized information in dimensional structures, and maybe call them quality dimensions to distinguish them from physical dimensions or mathematical dimensions or other types of dimensions. And they are sorted into domains. So the notion of a domain is very central to my talk here. There is the space domain that has 3 dimensions. I mean, the ordinary height, width, and breadth, depth dimensions. I will talk about color space in a while. There is shape space. We don't really know very much how shape space is organized, but we know that we can talk about similarities of shapes and categories of shapes and stuff like that. And one key notion here is that these domains are built on integral dimensions. And I have to say something about this distinction between integral and separable dimensions. This is a notion that comes from psychology. And dimensions are integral if you can't assign an object the value on one dimension without giving it the value on others. So take colors. Colors have three dimensions, hue and intensity and brightness. But if you can't have a color that only has a hue and no brightness and no intensity. So these three dimensions go together. Or if you take sound, you can have a pitch and a volume and maybe a timbre, and you can't have a sound without a pitch or a volume. So these dimensions go together. But if you talk about color, you don't have to talk about temperature, you don't have to talk about weight, you don't have to talk about volume. These domains are separable. They can be separated. And in psychology, this is a well-known distinction. There are several psychological tests for dimensions being integral. And from a mathematical point of view, when you talk about distances and spaces, a rule of thumb, but it's really only a rule of thumb, is that when you measure distances in integral space, then, or integral dimensions, then they combine with Euclidean metrics. That's not true because sometimes there are other metrics, but separable typically combined with city block metric or Manhattan metric. But this is just a rule of thumb, and don't take that too seriously. So I define a domain. This is my definition of the notion of a domain. It's a set of integral dimensions. So here are some examples of structures of domains. So the domains come with a topology or a metric. I mean, there are different levels of structures here. So here is a very basic type of quality dimension. It's a one-dimensional domain of time, and that's the structure of this is the structure of the real line. So you have an infinite future and you have an infinite past. I mean, this is an idealization, but that's how we represent time, at least in Western societies. And then if you take the dimension of weight, it's also a real line, but it's only the half, the positive part of the real line, because we don't talk about negative weights. So that has a different structure from time, but it's still a linear dimension. Then we can have the color spindle. I will have color as a typical example here. And we have three dimensions here. We have the hue, which is circular, red, blue, green, yellow, and back to red again. It's circular because we can talk about complementary colors, red and green, yellow and violet, and blue and orange, and so on. They are opposite each other on this circle. And there are psychological phenomena that tell us why we have this circular structure of the hue dimension. Then we have the intensity dimension, going from gray to more and more intense colors. And thirdly, we have the brightness colors going from the brightness dimension going from white to black. These three dimensions are not totally independent. So, and they are based on judgments of similarity. So when you get close to the white area of the color space, you can make fewer distinctions. I mean, it's difficult to distinguish a very, very light pink from a very light red. I'm sorry, that's a bad example. A very light orange from a very light red, that is, it's a pink. And similarly, in the dark area, the dark hues are very difficult to distinguish. So therefore, we get this kind of spindle model. So that's the color space, and I will say more about that in a while. Then we have the vowel space, and there are theories of vowel spaces that say that we recognize vowels by 2 or 3 dimensions. So here's a 2-dimensional representation. And the 2 axes are F1 and F2. And F0, and that's based on that vowels is built up from different formats. That is different frequencies of sounds when we produce the sounds. So there's the F0, which is the basic level of the tone. And the F1 is the first format of a sound, and F2 is the second format. So we can map these dimensions. And it turns out that we can represent different vowels by the relation between these formats. So these numbers are in frequency above the F0, and this is the frequency above the F0 as well. So you can see that we have the vowels are represented by these relations between the two first formants of a sound. So that's a fairly non-trivial example of a quality space. Roger Shepard proposed that we perceive harmonies in a torus. And I will not go into detail, but I just like this example because it's a non-trivial topology for a space. If you're interested, you can read more about harmony shape. But I just took these three examples as non-trivial examples of multidimensional spaces. And I could have talked a long time about shape space, but we know very little about the structure of shape space. So that's that domains are endowed with topology or metric. Similarity is represented by distance in conceptual spaces. And distance is inversely related to similarity. The more similar two objects are, the closer they are located in a space. And when I talk about conceptual spaces, I talk about human cognition, how we perceive shape, how we perceive color, how we perceive sound, how we perceive vowels, and so on. This is not scientific models based on frequencies or yeah, to some extent it's based on frequencies, but not on the physical representation. It's based on our perception of these phenomena. So typically you generate a conceptual space by starting by a similarity judgment. You have people sitting in the lab looking at different color chips and giving you information about how similar these color chips are. And then you take all this information, lots of people, lots of color chips, and then that has a high dimensionality, this data set. Then you use methods like multidimensional scaling or principal component analysis, and then you end up in a conceptual space that has comparatively low dimensionality. And if you're lucky, you can account for a lot of the data of the similarity judgments by a few dimensions. Of course, the more dimensions you use in multidimensional scaling, the more you will cover, but the less intuitive psychologically the space will be. So there is a bit of balance here between covering and simplicity, basically. Now, that's the background. I mean, this is a very short introduction to what I mean by conceptual spaces. I will probably say more in a few minutes, but I divide my talk into two parts. And that is, if you just look at concepts, some concepts are more natural than others. So the question is, what constitutes a natural concept? And I will talk about this in terms of design criteria. If you're an engineer and if you want to design artificial concepts, what criteria should you work on? Well, we can take that from the engineering point of view, but we can also look at human cognition and ask whether our concepts fulfill these design criteria. So I will build a parallel story here between what we would like to do as engineers when we create artificial concepts in robots or in AI applications and so on, or what we would expect from an optimally designed human mind or animal mind for that matter. So my basic design criteria that I presented in my Conceptual Spaces book is to say that a concept, a natural concept, is a convex region in a conceptual space. So convexity means that if one point, say the color red, if one object is called red, or one color is called red, and another color is called red, then anything in between is also called red. That's the definition of convexity. For any 2 points in a region, any point in between is also in the region. So I proposed this for colors. And I only knew a few languages where I could check it. Different languages carve up the color space in different ways. I mean, some languages only have 2 color terms, some have 5 or 6, and some have 11. I mean, there are very many different ways of carving up the color space. But I made a prediction that in all natural languages, the color words cover convex regions in the color space. And then Gerhard Jäger in University of Tübingen in Germany made a test. He checked, I think, about 110 languages that where we have the data about the similarity judgments of the spaces, where we know of the color partitionings. And he showed that basically all languages have satisfied this criterion of color regions being convex. So he gave me very strong support for this prediction that color terms represent convex regions of color spaces. But for most areas, we don't have the data. We can't check my prediction for many other areas. But basically, I still make the prediction, and we can discuss that maybe later if you like it or not. So why would convexity be a design criterion for concepts? Why would we like to have concepts that are represented by convex regions in conceptual spaces? For one thing, it handles concepts with vague borders. I mean, color terms are vague. I mean, there is no sharp border between red and orange or between red and violet. But convexity still applies even to vague concepts, because if you decide, even with vague borders, that this is definitely red and that's definitely red, then anything in between should also be definitely red. So even if you have vague models, convexity still applies as a criterion. So we can explain the vague borders. We can model that with membership functions and so on, and convexity still applies. Then a more important aspect that it connects to prototype theory. So probably know about prototype theory, that within many domains we have more or less typical examples of concepts. So a robin is more typical bird than an ostrich, and so on. An apple is more typical fruit than kiwi. Eleanor Roche in the 70s showed that for many domains we have this kind of prototype structure of concepts. If you go back to the symbolic traditions, they mainly worked with the Aristotelian criteria, necessary and sufficient conditions, but in psychology that doesn't work. Roche's prototype theory was a much better description of how people categorize things. And if you represent concepts with convex regions, then the prototype is more or less the central point in the region, in this region. So we can have a nice connection here. It's known from psychology that children learn the prototypical meanings first when they learn about new concepts. That was one of Eleanor Roche's criteria for something being prototypical. So if you have a space, now I illustrate this with a simple two-dimensional space, and if you have a number of prototypes, these are the red dots here in that space. This argument generalizes to any number of dimensions, so it doesn't matter where you have two-dimensional space here. If you have the prototypes, then you can classify any point in the space by saying that it belongs to the category that is defined by the closest prototype. So for any point, you find the closest prototype, and then you say, this is the category the concept belongs to. And that rule, sorting points with closest prototypes, generates what's called Voronoitessellations. And it's very simple to show that these Voronoitessellations, I mean, these are marked by if we have sharp borders, you will get these lines here. They generate convex regions. So having prototypes, going by the closest prototype, you generate a convex partitioning of the space. Sometimes the prototypes may be very similar to each other, like these 2 points being close here, and then the prototype will not be in the center here. And my intuition, and I hope your intuition, says that this is a less natural classification than this one. This is more natural, and I'll get back to this criterion. How can we decide whether that this is a less natural partitioning of the space than this one? Both in this toy example is based on a set of prototypes, but maybe we don't find prototypes structures like in this example. This is maybe a more natural way of finding natural type of prototype distributions in the conceptual space. I will get back to this point in a while. So it connects to prototype theory, and also a good advantage of conceptual spaces compared to symbolic representations, compared to neural networks or connectionist representations, is that we can explain quick learning using conceptual spaces. So I will give you a toy example here. So suppose you are a father walking with your daughter in the town to the town pond, and there you find some examples of ducks. You find some of these dots are the ducks you have seen, and you have, this is bird space. And you find some examples of geese, and you find some examples of swans. So these are the dots here. And they have different properties. Bird space is probably multidimensional, not just two-dimensional. My toy example depends on being, I must be able to show it on a two-dimensional surface here. So the daughter sees a couple of examples. The father says that this is a duck, this is a duck, this is a duck. Based on these examples, the daughter extracts some kind of mean value. And here I'm taking the simple mathematical rule that we form the mean value of all the examples we've seen, and that's the cross here. And that's the mean value of all the geese, and that's the mean value of all the swans. And then we say that for the time being, the child views this as the prototype of a duck, a goose, or a swan. And based on that prototype, you divide the space into three. You take the Voronoitesselation, you divide it into three regions. And then you can, if you see a new duck that has these properties, if you end up with a bird that has properties down here, you know the closest prototype is a duck, and the child can happily say that it is a duck. But reality is not always simple. So sometimes you see a new thing. It's an odd duck. We can say maybe it's a mandarin duck. It's a kind of strange duck. And the father insists that this is a duck. I mean, the hatched lines here are the old prototype. That's the old, the Voronoitesselation. But based on this new example, we get a new mean. The child moves implicitly, I mean, not consciously, moves the prototype here, and we get a new partitioning where this one will now be a duck, and the border towards the geese will be moved a little bit. So even after very few examples, you will be able to form a mean of what you have seen. That mean can serve as a prototype, and you go on and use the means to classify new examples. Sometimes the classification will be wrong. You have to relearn, you have to adjust your prototype. But this is how concept learning works. The concepts are not fixed. We adjust the borders depending on our experiences, depending on feedback, linguistic feedback, and other feedback from our peers. So, but anyway, we don't have to have extensive data exposure in order to generate concepts. Once we have the dimensions given, I mean, that's a big if here. Once the dimensions are given, then learning is very quick. So conceptual spaces have this advantage of explaining how learning can go quickly. Then it also provides a model of how generalization works. I've already shown you how it works. I mean, once you have the regions, you can generalize it to new items. But you can generalize in different ways. And there are, in psychology, people talk about what I call generalization gradients. I don't want to get into this, but sometimes you generalize wildly. I mean, you call everything a dog that looks a bit like a dog, but maybe sometimes you have a more narrow generalization gradient going from the prototype and towards borders. And sometimes you have a very narrow gradient. You only accept a few items as being generalizable there. And psychologists have investigated these generalization gradients in great details. I don't want to get into this topic, but basically we can explain it using the conceptual spaces modeling and the Voronoitessellations here. And this mechanism of generalizability, the quick generalizability, is a problem both for the symbolic representations and for the connectionist representations. Now, this was my proposal in my book, that concepts are convex regions in some conceptual space. And I said this is a necessary criterion, maybe it's not sufficient. And so what other criteria would you like to have for concepts represented in conceptual spaces? So some years ago, I joined efforts with Igor Doen, and we published a paper last year where we proposed some further design criteria. So here are some further criteria, and that's one is parsimony, that we should have not too many concepts in a region. You shouldn't have too many color terms, or too many bird terms, or too many categories, because then you have to learn not a lot of prototypes. You have to, that would be a load on memory. So in order not to overload your memory, the conceptual partitioning should be parsimonious. Now, the other criterion that somehow goes against this one is informativeness, that you should have concepts that are good enough to give a conceptual coverage of the domain of classification. Now, the main purpose of having concepts is that you use them to act. You sort things into edible things and non-edible things, and depending on whether you like something, whether something is edible or not, you act accordingly. You sort things according to their function, and depending on their function, you act differently in relation to the object, and so on. So you want a concept partitioning to be informative enough to help you in selecting the right action. And in a sense, this is in contrast to the parsimony requirement. And you have to find a balance that is optimal here, that is parsimonious enough to not overload your memory, but is informative enough to help you in finding the right action. And how this problem is solved is not a simple problem. It depends on how fine guidance you need to your actions. So if you're an expert in an area, you need further partitionings. You need fine partitionings. If you're a layperson, you don't need such a fine partitioning. So there is no universal answering to how to handle this balance. It depends on the needs of your activities. Third criterion is that the concept should be in contrast. It should be easy to separate two different concepts from each other. They should be easy to tell apart. So that's the third criterion we proposed. And then the final criterion here is what's called Wellformedness, and maybe that's a criterion that covers all the previous ones, or is a kind of maybe an optimality criterion. And this is proposed in a paper by Terry Regier and some of his co-authors. I'll give you the quotation soon. So they say that a concept should be well formed. So the following items falling under one of the concepts could be maximally similar to each other and maximally dissimilar to items falling under other concepts in the same space. So in this respect, this partitioning is more well formed because the items here are more similar to each other. Here, these items are very similar to each other, and this partitioning doesn't satisfy the criterion of contrast, because here to these objects in this area, they will be classified either as this prototype or with this prototype, even though they are very similar. So the contrast here is quite low in this one. So this partitioning is not optimal from a design perspective. This is not optimal either, but it's a much better partitioning from the point of view of being a well-formed concept partitioning. So Greger, Kay, and Ketapal define well-formedness, define a measure of well-formedness in the following way. So they have a measure of within similarity, which is that for any 2 points that are assigned the same region in the partitioning, they sum the similarities. So the more similar they are, the greater will this similarity be. And then they have a cross dissimilarity, saying that for any 2 points that belong to different categories, you measure the dissimilarity. That is 1 minus the similarity here. We assume that similarity is between 0 and 1. And so the more dissimilar they are, the greater this will be. And then they simply say that the well-formedness is the sum of the within similarity and the across dissimilarity. That's their definition. But you may as well just use the entropy. There you can define an entropy measure quite easily on a partitioning. And that will also give you, the minimum entropy is I'm sorry, maximal entropy is a good measure of well-formedness of a partitioning of a space. I don't know how different the entropy will be from this measure that they Kay and co-authors proposed here. So we can have, I mean, given a space with a metric, we can measure its the well-formedness of a partitioning here. So just to give you an example from their paper, they took the color space and then you could have the color space partitioned into 2 or 3 or 5 or 4 or 5 or 6 different areas. And if you take 6, you get the 6 main colors, that is yellow, red, blue, blue, green, and black and white. White is here represented by gray, otherwise it can't be seen. So this is, then they calculated within this color space, you have the distances within the color space, and then I calculated the regions within this color space that would give the most well-formed partitioning of the colors, given some basic prototype of these colors. And this is the same picture, just seen from the upside down. So here black is at the top and white is at the bottom. It's basically the same color space. So this is their calculation of how color space would look like. Then you can compare that to a language where we have these 6 basic color terms and see how well the language fits with this kind of most well-formed partitioning of the space. So that's the design criteria applied to color spaces. That's their main example. Okay, that's my description of design criteria for color spaces. Now I've been talking quite generally about spaces, one-dimensional, multi-dimensional spaces, about convex regions and spaces and so on. I've given you some examples, mainly color examples here. Now I want to apply this, but to a more linguistic description of concepts. So now we get to part 2 of my talk here, and that is designing concepts for natural language. So I first of all want to make a distinction between, this is my distinction, it doesn't exist in the literature in general. I make a distinction between properties and object categories. And properties are convex regions in a single domain. So we can take, the colors is an example here. And then I say that in natural languages, we typically, I mean, not in all languages, but at least in the European languages and many others, properties are described by adjectives. And that's the role of the word class of adjectives to describe properties. And so I formulated this, what I call a single domain constraint for adjectives. The meaning of an adjective can be described as a convex region in a single domain. That's a fairly strong prediction. It's an empirical prediction. It can be tested once we have domains identified. There are probably exceptions to this, but still, it's a rule of thumb that I think helps you quite a lot in understanding the meanings of most adjectives, in particular adjectives having to do with perceptual and bodily categories. So the adjective heavy lives on the weight dimension, hot on the temperature dimension, bitter on the taste dimension or taste domain, and round on the shape domain. I haven't given you what the shape domain is, but we still can talk about more or less round things and so on. That's a shape category here. And if you just take the temperature dimension, we can divide them into hot and cold. And typically, we talk about hot as being the upper third of the temperature dimension, and the cold as the lower third of the temperature dimension. What is the upper third and lower third is context dependent. So there is no unique degree or anything like that determines what is hot and cold, but that's dependent on the context. Some languages have a mid word for the middle, and in English we have this lukewarm, but not always. All languages have this term. Now, my single domain constraint has a lot of predictions, as I said. So it says that convexity means that no adjective means green or orange, because green or orange is not a convex region. And I still haven't found any really convincing example of a color term in any language that is non-convex. So color terms or adjectives, they are convex. So that's something that is an empirical prediction. So that means a color term that is green, means green or orange, is a non-natural term. Yeah, and I would consider it odd. It also has this single domain constraint has the prediction that no adjective means long and hot, because that is something that covers two domains, size and temperature. And there may be exceptions to this, but in general, almost all perceptual adjectives satisfy the single domain constraint here. So by having these constraints, single domain plus convexity, we can exclude a large amount of non-natural concepts. And the prediction is that most adjectives in natural languages will satisfy these constraints. So that's adjectives. Now we get to object categories. And an object category, like a category of a tree or a dog or a chair or any ordinary material object, is something that has properties in several domains. So a dog has a size and it has shape, as a temperature, as a weight and a volume, and you name it. It has a color and a sound and it has a lot of properties. So they have regions and different domains. I still claim that objects correspond to regions here. And some of these domains are more important for categorize something as an apple or as a dog or as a tree and so on. So the domains have different prominence values. And then the domains are correlated. So to show this, I'll make a simple experiment with you. So now be prepared. Show me how big with your hands. Show me with your hands. How big is a spoon? Show me. I see a couple of you. I mean, show me with your hands. How big is a spoon? Yeah, okay. I would guess that most of you would have approximately 20 centimeters, 25 between your fingers there. Now we take the second part of the experiment. Show me how big is a wooden spoon. It's bigger, isn't it? Yeah, it would be 30, 40 centimeters. So there is a correlation between the material of a spoon and the size of a spoon. There is a correlation between the sound of a dog, the size of a dog, there is a correlation between the color of an apple and the sweetness of an apple. We have correlations between properties, and we know them implicitly. I mean, I took this simple example just to show that you know these correlations. You can answer questions about them quite simply. So this information about domain correlations is also part of object category concepts. And typically, object categories are expressed by nouns. I'm not saying that all nouns correspond to object categories, because there are all kinds of nouns, and I don't have time to get into these other categories. But basically, we can take the simplest example. And when children learn words, they learn the words and the nouns for object categories first. So in that sense, they're primary. So here's a very simple example. My toy example is apple. So you have well, let's take color first. I mean, they're red, green, and yellow. There are no black apples, there are no blue apples, and so on. No gray apples. Maybe apples can be brown when they are rotten, and so on. Taste, you have four-dimensional taste space: sweet, sour, bitter, and salty. When it comes to apple, it's mainly sweetness and sourness that are involved. The shape is round, whatever shape space is. You can talk about nutrition and so on. You can talk about more other fruit dimensions that you learn when you become an expert. But when you're a child, you learn basically these three domains: color, taste, and shape. These are the first domains you learn about. You learn about the domains here. You learn about the correlations that red apples are sweeter, and so on. Then you can, when you learn more about the concept, you can add new domains like nutrition and so on. So concepts are not fixed. You can learn more things about them, and you can learn more about what regions are covered and so on. But that's still a toy example, and I don't want to get into details here because I can't give you the details, basically. So I've now said something about that. We map properties onto adjectives. We map object categories onto nouns. So these are the basis for some of the word classes in our language. I'll say a few words about verbs and prepositions as well. But this is basically what I do in the second part of my second book, The Geometry of Meaning, to give a foundation, a semantic foundation of word classes. Linguists, they give syntactic definitions of word classes. I think, I shouldn't say it's a mistake, but cognitively, we need a semantic definition of word classes. And so that's what I've tried to do here. So I've been giving you some hints on how to handle adjectives and nouns. Now let's get to verbs. And verbs are related to dynamics domains. It goes back to Marr and Weina's analysis of walk here. They break down the body into parts, and they break down the arms into further parts, and so on. So there is a hierarchy of body parts. And then you have, they do it with differential inequalities here. I do it in a slightly different ways, but basically it's the movements, or in my case, well, let me give you an example of how easily we categorize actions. So maybe you don't see what this is, but I give you 200 milliseconds of here. So after 200 milliseconds, you immediately see that this is a person walking. So what you don't need anything about the size, you don't need anything about the color, you don't need anything about the weight or the temperature or the surface structure. You only need the information about the body parts of this individual in order to classify the actions. You see it very quickly, very efficiently. So based on data like this, I propose that what we see here is not just the movements or the differential inequalities here. We see a pattern of forces. We are good Newtonians, and we extract the second derivative of these movements, and we extract the force patterns behind these movements, and we represent the actions by these force patterns. That's my hypothesis. I have some evidence for it. I would like to have much more evidence, but I'm working on it. And we can also show that these force patterns, I mean, these movies I showed you was taken from Paul Hemmeren's PhD student, the former PhD student of me. And he showed that we can find prototypical movements. There are prototypical ways of walking. There are prototypical ways of throwing their prototypical ways of kicking and so on. So we have exactly the same prototype structure. He checked all the features of Eleanor Roche's prototype theory and found them in action categories. So they have these prototype structures as well. And I propose as a hypothesis that an action concept is a convex region in the space of force patterns. I owe you the definition of the space of force patterns, but I think I can formulate it. And basically, I have an analogy. I mean, shape is a kind of patterns in the ordinary physical space. And I say that action is a kind of similar kind of patterns in force space. So I take actions as a parallel to shapes, but in force space instead. In force, dynamic force space. Okay, so let me show you an analysis that we did in robotics. Another PhD student of mine who developed neural networks for categorizing actions. So what you see here, I should stop the movie. This is the input. That's Kinect data from a movement of a person. And this system was done to categorize actions in real time. So the movies I show you are slowed down so you can see the movements. And then we trained the system on 10 different actions. Here you see something, you will see names here. So you will see things like waving front, tennis swing, and high wave, drawing a cross and so on, drawing a circle. There are 10 different actions. And when the system, the neural network, sees this Kinect movements, it has been trained on these 10 actions. And then you see the activity here. Here it guesses what is the most likely action that it's seeing. And up here you see the desired output. And at the end, you will not see the final output here, but during the time period of an action, you will see the most guessed action here will be the output. So now I play a part of the movie here. So now you see these are the activities of the different actions, and now it guesses that it's a front wave, but later it will guess something else, I guess, when it sees more of this, still a front wave, then it guesses something else. I don't remember the movie actually. Yeah, no, this ends up with a front wave, I guess. These are guesses coming out from the system. Now we turn to next action, that is a tennis swing. So now it will guess, it sees the tennis swing. Sorry, I stopped the movie. Come on. Yeah, so now it guesses here. Oh, sorry, we get on to draw a circle. Yeah, it guessed to draw a hammer first, but that was wrong. Then it guessed high wave, and as it goes on, it guesses something else. I hope it guesses draw circles finally, and so on. You see how the system works, and we got the categorizations more than 90% right after a lot of training. But the point of that this was done in an artificial system in real time, so it could categorize actions. And we need a lot more data, lot more training to get other kinds of actions to be done here. But basically, we have a system for identifying the movement patterns in real time here. Sorry, I should stop the movie and go on. So we use this categorization of actions to represent verb meanings. And there are two kinds of verbs, but for both kinds of verbs, I make the single domain constraint for verbs here. So a verb root, I mean, there are all kinds of inflections of verb, is a convex region of vectors depend on only a single domain. But there are two types of vectors. There are force verbs. So push is a force vector, and it refers to the force domain. Move is the result of pushing, and it refers to changes in the location. So that's a change in the spatial domain. And if you take a verb like heat, it refers to changes in temperature. So most simple verbs represent changes in one domain. And in linguistics, you can distinguish between action verbs, and they are represented by force vectors, and result verbs, and they are represented by changes in some other domain. There are, in some more or less perceptual domain. So again, this prediction has consequences. There is no verb that means walk and burn because they're two different domains, and there is no verb that means crawl or run because that's not a convex region in the force pattern space. And again, that's an empirical prediction. I have to speed up now because I'm soon running out of time, so I will just give you a very quick thesis for prepositions. And again, you will see that there's a pattern to this. There's a single domain constraint for prepositions. They denote convex regions in a single domain. And again, there are different domains here. Most prepositions refer to the spatial domain above and so on. And some linguists have said that all prepositions are spatially grounded. I don't agree. Some prepositions like depend on the force domain, like over or on. Some prepositions depend on the time domain, like before or after or during. And some even depend on more abstract domain, like epistemic domain and so on here. But still, prepositions refer to a single domain. I don't want to get into the distinctions between prepositions and adjectives, but there are distinctions here. Then prepositions are very often used metaphorically, and that makes this mapping a little bit more complicated. That's all I have time to say about prepositions. To summarize, I have identified what we can call semantic structures of word classes. So adjectives are regions of single domains. Nouns are regions of products of domains, together with prominence values, together with information about correlations between the domains. Verbs are vectors vectors in domains, I should have written here, either the force domain or other domains. Prepositions are regions and vectors. There are vectors also. There are the direction prepositions. I haven't had time to give you the details here. The distinction between prepositions and adjectives is that prepositions are relational. They're relational with respect to a landmark. Adverbs I don't want to talk about here, but they function as multipliers. Demonstratives I could give an analysis of as well. Quantifiers are properties of sets. Don't ask me about the details. But basically, we can distinguish. This is a semantic definition, semantic characterization of the different word classes that we find in many languages. I'm not saying that all languages have these word classes, but Indo-European languages have them at least. Yeah, so that's the end of the second part. I don't want to talk about my analysis of events because I have an analysis of sentences as well. But maybe we can do that in the discussion. So my take-home messages for if you want to build artificial systems for robotics, for AI, and so on, there are some things I think you should adhere to. I have given you criteria for the naturalness of concepts. It's good if you can define systems that generate conceptual structures that satisfy these constraints. So in order to do that, you organize information in separable domains. Maybe the best way to do it is neural networks. Probably the best way to do it is neural networks with some on top structure, with some additional structure, but I don't know exactly what that would be. If I knew, I wouldn't be sitting here. Then, of course, based on this information you get, you need some kind of measure or at least nearness judgments in order to generate the divisions of a space into or division of domains into regions. And you need to identify prototypes, but if you have the prototypes, then you can speed up the learning of the system. You can speed up the finding the borders between the generalization and finding the borders between the concepts. And then, of course, using a neural network or some other method, you should learn the correlations between the domains if you are dealing with the object categories, because that's very important information. So these are some rules of thumbs for people working with conceptual engineering. I mean, really wanting to construct things. Yeah, so I've taken this theme of the workshop seriously and really try to talk about conceptual engineering. It's a vast field. These take-home messages are just rules of thumb. And as I've tried to show you, there are lots of things that need to be done in order for us to understand how to build a good artificial conceptual system, or how we should proceed in order to how we can understand how humans and other creatures do create concepts in their minds. So thank you very much for listening to me, and this is the end of the talk.